G'day Year 9s, welcome to our first lesson for Unit 4 of the year. It's radioactive. We're going to be looking at some radiation and learning about what that is. So our first lesson is on the structure of the atom. We did a little bit of it last year in Year 8 chemistry. Now we're going to start looking at it a bit deeper, and so now we're dealing with it in terms of physics, because chemistry gets at the macro stage with electrons and interactions, and then anything smaller than that, they generally just go, nah, the physicists can deal with it. So we're going to do a little bit of physics of the atom. So here's our Walt and our Wilf. So we're going to firstly have a bit of a quick refresher, what's inside an atom so that we know where we're at. We want to know the structure, we want to know the definition, and a couple of things you should be able to do is, well, what's the 3 subatomic particles? And then we want to know what an isotope is, because that's going to be really important for our topic of radiation. Oops. So radioactivity, the reason we're doing this is that radioactivity is a bit of a big question for you in your day and age. Nuclear power is something that is very commonly discussed as a possible power source to be used. Radiation is used quite extensively in the treatment of cancers, and we use it a lot in terms of, what's the best way of explaining it, archaeological finds, a lot of medicine, power sources, even some of our engineering type things where we're looking at structures of metal and the strength of materials, deal with radiation and finding out things using that as a tool. So you probably want to know a bit about it because you're going to have it in your day-to-day life going forward. It's also really important to differentiate between radioactivity and the radiation that comes out of that, and other forms of radiation like 5G towers, for example, which are a completely different type of radiation. And when we deal with electricity and heat later on this year and next term, that'll be more important there. So, bit of a recap. Everything is made of atoms. We learnt this last year. Everything around you, my tablet, my pen that seems to be a bit wonky, my fingers, the table that this is resting on, my headset that I'm speaking into, everything is made up of atoms. They're made up of combinations of different atoms. So my computer has a fair amount of plastic on it, but it's also got a lot of silicon, which is another type of atom, and it'll have other types of atoms, probably a bit of gold because it's a very good conductor, likely a few rare earth metals, copper it would probably be a big part of it as well. My table is made of wood, so there'd be a lot of carbon and hydrogen and oxygen in that. Remember, an atom is the smallest piece of an element, and an element are the different things that exist in the world around us. If we cut it any smaller than that, it's no longer the same element, because if we separate the center of an atom, if we separate it into 2 smaller pieces, we get different types of elements. Okay, so an atom is the smallest type of a particular element. Here are some common examples. Carbon, oxygen, a couple of those we just said, neon in the lights, uranium you might have heard of, cobalt is a lovely silvery blue metal, hydrogen, stuff's everywhere, it's kind of the hussy of the universe, and you'll notice each of them have their own symbol. It's important to remember that as well. You don't need to memorize any of these. By the end of year 10, the syllabus generally requires that you memorize up to element 20 in terms of their names and their numbers, just so that you can recognize, if given the name, what's the letter representation, if given the letter, what's the name, and if you take senior chemistry, you go a little bit further past that as well. But while more often than not you'll have a periodic table, if you need to work with elements, it can help just to recognize a few common ones, especially the ones that make sense. So let's talk about inside the atom. What's really fascinating, and I want you to take a quick look down at yourselves here, the atom is 99% empty space, which means you're 99% empty space. And the chair you're sitting on right now is 99% empty space. But everything looks pretty solid. I mean, I poke myself and, my finger goes into the gut here. I have thanks to my wife's cooking, but, it doesn't go through it. I can't stick my hand through and have my fingers pop out the back and give it a bit of a wiggle. So we say how do we know it's 99% empty space? Well, that's something we're going to explore over the unit, but for now, you're just going to take that as a little bit of information. So the structure is made up of core, called the nucleus. You may have heard this last year. And then around that nucleus are little tiny electrons. Okay? And they orbit. Now this diagram is kind of a very, very simple first level model. And the reason I start with this one is we can see A, we've got our nucleus here in the middle, and B, we have some electrons that are much smaller whizzing around it. It does have a lot of limitations, and we will delve into the structure of an atom and how to properly draw electrons and nuclei and stuff like that throughout the rest of Year 9 and into Year 10 a lot as well. However, this is a good starting point, the idea of bit in the middle and bits going around it. Now let's give you an idea of how to imagine that. Now, we're imagined at school, so there's your first imagination, but you've got an apple. That apple is in your hand. Now, if you had a grape all the way over at Indooroopilly Shopping Centre, that's about the distance, if we scaled it up, between the nucleus and the electron. Okay? For a similar sort of scale perspective, let's say if you had a watermelon at school and or maybe an apple at school, and you had a pea over at Civic, that might be another good sort of representation of scale there as well. Or perhaps a grape to a pea, probably actually less than a pea, let's say a grape to a grain of rice between the school and the Civic. Okay, I'd have to do the math to check the ratios exactly, but I just really want you to get in mind how far apart these things are. Okay, so there's a lot of empty space, and I don't mean empty space as in, oh, there's air in there, because remember, air is made of atoms. I mean nothingness. Okay, there is absolutely nothing between this central nucleus, and we're going to see what they're made of in a second, and that first electron. Okay, so let's delve a bit deeper. What's inside the nucleus? The nucleus has two things hanging out in it. One is called the proton, and the other is called the neutron. They're about the same size. The neutron is just a little bit bigger. It's like if you had an identical twin and then that identical twin ate all the cupcakes, they'd be just a little bit bigger than you. Okay? So they hang out in the middle. This is a better version of a diagram of the atom. So here we can see our protons and neutrons. Note the protons are kind of spread out. We'll get to that in a second. And the electrons you can see here are sitting on rings around it, which again is a better representation of some of the stuff we'll deal with in chemistry later this year. Now, these particles that we're going to be talking about have a property called electric charge. And you might recognize they're connected with electricity, and they are. We'll talk about that in term 3. However, something to keep in mind, to understand what electrical charge is it's kind of like magnetism. And if you take physics, then you'll learn about the connection between electricity and magnetism. But if you've ever played with magnets and you've felt how you've got a north pole and a south pole, and if you get two magnets, the two norths push against each other, but the north and the south pull against each other. Magnetism and electric charge behave the same way, but they're different properties. Okay, if you have two positively charged things, they don't like each other, they push away. You have two negatively charged things, they don't like each other, they push away. But if you have a positive and a negative, hey, they like each other, they pull together. If you have a positive and a neutral though, the neutral is not attracted or repelled. Two neutrons, a neutron and an electron, okay, these things just don't care. Okay? There's a little bit more than that, and when you take senior physics, notice I said when, because we should. This is all explained a bit deeper in terms of other types of forces. But to begin with, we're just going to deal with electrical force and electric charge, and there are 3 types. The proton is positive. I always remember P for proton, P for positive. Straightforward. The electron is negative. Okay. and the neutron has no charge. So neutron, neutral. You can see that there's the same root word there, which is why it was called the neutron, because they knew about protons and electrons, but neutrons were discovered later on, and once they go, oh, it's got no charge, we'll call it a neutral particle. The fact that we call electrons negative and protons positive is complete, just 50-50 chance. Ben Franklin went with the idea of kites getting positively charged in storms, and because of that we've kind of been stuck with the idea that protons are positive and electrons are negative. Trust me, if you'd done the other way, it would have made some of the math a lot easier. So to summarise it, here's a nice little summary. We've got a neutron, it's got large, it's no charge. Proton, large and positive. Electrons are very, very, very small, and they are negatively charged. Okay, now there's a great video on my OneDrive. Feel free to have a watch of that video. And if you're watching this from YouTube, you can find Crash Course on Atomic Structure on YouTube. Great series of videos. So let's talk about jobs, because these combinations of particles make up different stuff. So the proton makes an atom what it is. If you've got 6 protons clumped together, doesn't matter what else you've got. If you have 6 protons, you've got carbon. If you've got 8 protons, you've got oxygen. You've got 92, you've got uranium. Lead, I think, is like 82. Gold is 80, somewhere around that region. Mercury, I believe, is 81. So the number of protons makes something what it is. If you can add a proton to something, you will change the element. So if you think back to the alchemists of old, if you've ever heard of an alchemist, they were very obsessed with trying to turn lead into gold through chemistry. You can't do it through chemistry. You have to do it through nuclear physics. So we can take a bit of lead and we can stick it in a particle collider, and we can shoot things at it to try to knock 2 protons out of it and turn that piece of lead, that single atom of lead, into an atom of gold. And we could do that lots of times and turn lead into gold. It would be exceptionally expensive and take more energy than I think the universe has in order to do it for a few kilograms of gold. However, we could do it. It just wouldn't be cost effective. But the opposite is also true. Lithium, down here, you can see has 3 blue dots. Yeah, it looks like they could be using blue or yellow for the protons there, but let's say that's the blue ones. If we jammed another proton into it, it would become beryllium. Okay. And we're going to see some examples of that later on in the unit, where we will build some atoms using simulators and see what happens when we add more protons to things. So a proton makes an atom what it is. The neutron is at this stage a spacer. Okay, remember we said that protons are positive. If you put 2 positive things near each other, like we can see here in my lovely picture from Saturday morning breakfast cartoons, the protons don't really like each other. Okay, there is a little bit extra going on here, but that's for year 11 and 12 nuclear physics to deal with. If you're curious, come and talk with me and I'll explain it. Okay, but as you get closer and closer, they hate each other more and more, and the neutrons kind of act as spacers to keep things stable, which is going to be really important. And then finally, the electrons. Now, electrons are all about bonding. They're about joining up, making new and interesting things. If carbon atoms didn't join together to make big, long chains of stuff, instead of having cool things like us, there'd just be atoms of carbon floating around. So electrons are pretty important, but electrons are all chemistry. So right now, at this very day, all you need to know, because we're not going to deal with anything more about electrons apart from when they get shot out or sucked in on radiation, is that electrons help atoms bond. That's it for now. We're going to do chemistry on electrons in term 4. So now that we've covered our 3 types of atoms, we're going to talk about special types of atoms called isotopes. If you have one proton, you have hydrogen. Doesn't matter what else you have, if it's got 1 proton, it's hydrogen. In your body, you have trillions and trillions or most likely of hydrogen atoms, since it goes to water, and you've got a lot of water in you. Remember, H2O, there are 2 atoms of hydrogen. But maybe 1 in a billion, 1 in a trillion, okay, of those atoms of hydrogen are a special type of hydrogen. It's called deuterium. And we give it a special name just because it's really useful, so rather than calling it the very boring hydrogen-2, we give it a cool name. Deuterium, okay, is a hydrogen proton, one proton, with a neutron. Right? It's slightly heavier. That's why, if we make water that specifically has a higher proportion than normal of deuterium, it's called heavy water. Deuterium, kind of useful. We do things with it, and we'll get into that later in the unit. But chemically, it's the same. Okay? Your body takes in water, uses it for certain chemical processes. We could take, if it came in on a sugar molecule that was broken down, and you end up making some water with it. Well, that water could have a heavy hydrogen, and it would do exactly the same stuff with it as if it was a normal hydrogen, or at least, or I say normal, but what I mean by here is the common version of hydrogen, because this is a lot more common than that version is. So chemically, your body can't tell the difference. Okay? In fact, you have some potassium in your body right now. Potassium is another element. You get it from bananas. That is perfectly fine. But some of your potassium is an isotope that is radioactive. So you are radioactive. And there's a few of these in your body. We're going to learn about those as we go through. Okay? Chemically, no different. But on a nuclear scale, on the scale of nuclear physics, down at the nucleus level, okay, they are different. And we call these different versions isotopes. So these are both isotopes of hydrogen. There's another isotope of hydrogen called H3 or tritium, which is radioactive and a little bit dangerous. Okay? So as we just said, isotopes, they are the same chemically. Okay. However, they are radioactive, and so they can be used for jobs, medicine being a big one, and from that is going to be the big basis of our unit. Okay. Yeah, we'll leave it at that because we'll talk more about deuterium as we go through the rest of the unit. Okay, that clarifies our first things. Just a couple of reflection questions, which are on our e-learn for this week, as I recollect. List the 3 subatomic particles. Tell me where you find them. Okay. Explain the jobs and describe how isotopes versus normal atoms differ. Those instructions, I do believe, are on our learning at home week for e-learn. Anyway, thanks very much for listening, guys. Have a great evening. Bye.